For a robot to navigate a space, it must first establish its coordinates within a digital map. Within the ROS2 ecosystem, developers typically manage this requirement using the Navigation 2, or Nav2 stack. Nav2 is designed as a modular but highly integrated system, often bundling localization, cost map generation, and path planning into a single launch sequence. This integrated design is helpful for standard deployments, but it can be restrictive for developers who need to implement specialized path planners or custom control logic. To gain more control, we are going to separate the Nav2 components, extracting only the localization engine to serve as a standalone module. By stripping away the default planners, we can feed location data directly into our own custom algorithms, allowing for more specific navigation behaviors. The default Nav2 architecture tightly couples localization with cost maps and standard planners. Our approach is to isolate the AMCL localization module and remove the rest. We then route AMCL's output into a custom pipeline containing our A-star planner and cubic spline smoother. In this configuration, AMCL has a single responsibility, providing the robot's X and Y coordinates on the map. It also calculates theta, which represents the robot's current heading or orientation. This coordinate data is published to the /AMCL pose topic. This topic provides the spatial reference used by the entire custom stack. If this stream is interrupted, the custom path planners have no way to calculate a valid route. To understand the reliability of this data, we must look at how AMCL derives those coordinates. Everything begins with a 2D occupancy grid, where white pixels are navigable space and black lines are walls. The robot's location and heading within this grid is its pose. To estimate this, AMCL scatters hundreds of particles, each a probabilistic guess. Every particle is an independent hypothesis of where the robot might be. As the robot moves, its LiDAR sensor measures the distance to the walls. AMCL compares these live measurements against the map, discarding hypothetical locations that don't match. By combining this with wheel odometry, the remaining particles cluster around the actual position. This becomes a rigorous process of mathematical elimination, repeatedly culling impossible locations until the most likely pose is identified. Transitioning this theory into a running system requires launching the localization node through the terminal. This command initiates the localization sequence while keeping the rest of the Nav2 stack inactive. The first argument dictates the map. You must provide the full directory path to your pre-generated YAML file, or the filter will fail to initialize. The second argument sets uSim_time to true. Because the Turtlebot 3 runs in Gazebo, AMCL must sync with the simulation's clock, not the computer's system time. At this point, the software is active, but in a symmetrical or repetitive environment, the filter may not be able to differentiate between similar-looking areas. This leads to a common challenge in robotics, known as the kidnapped robot problem. In a square or repetitive room, the LiDAR data at one corner looks identical to the data at another. Because several locations appear equally valid, the particle filter cannot converge on a single estimate. To solve this, the filter requires an initial seed to narrow down the possibilities. We provide this initial estimate manually using ROS2. This demonstrates that even automated pipelines often require a human-provided starting point to successfully link the digital map to the physical world. To seed the system, navigate to the top toolbar in RViz. Select the 2D Pose Estimate tool. Click on the map at the approximate location where the robot is currently positioned. While holding the click, drag the cursor to indicate the direction the robot is facing, setting the theta value. This view in RViz shows the result. The green AMCL particle swarm appears immediately around the robot's footprint. You can watch the particles converge, snapping together as the algorithm confirms the robot's position. This dense cluster is the visual confirmation that the filter has successfully synchronized the sensor data with the map. With the position confirmed, the AMCL node begins broadcasting continuous coordinate data to the /AMCL pose topic. With localization isolated and the pose verified, our custom A-star planners and controllers can use this data to take command of the robot.